Oh, I didn't put this, I didn't have a special slide for this. Actually, let's let it go at that. I think maybe this is enough to say about the categories, because if you absorb this point, that's already good. I mean, on my outline, I had that thing about the junction, but it's good enough if you get this. So, what are foundations for anyway? What are foundations? And it's a good question. It's a very good question. I'll tell you, Penn Manning has an article that she has written for a book. It hasn't appeared yet, where she says it's generally agreed that Zermelo-Fraenkel set theory with choice is the foundation of mathematics, but surprisingly, there's less agreement about what this means. Well, I don't know that that's so surprising. It's very easy to get people to agree if they don't have to know what they mean by the agreement. It's harder if they do have to know what they mean. Thank you so much. Yeah, this is his. Zermelo was clear in 1908. This is, I believe this is the second important paper that Zermelo wrote about set theory. I believe he wrote his first important paper in 1905 and his second in 1908, where he tries to give a clear axiomatic basis for set theory. Cantor had developed lots of theorems of set theory, except that he didn't give axioms. He really didn't give theorems of set theory. He gave arguments about what should be true, but he didn't give specific axioms and then proofs. He gave some very careful arguments sometimes, but he hadn't picked what the axioms were. Zermelo then gives specific axiom and says, by a proof, I mean a proof from these axioms, and I can prove this from these axioms. He was concerned with the axiom of choice. Is the axiom of choice true? For Cantor, that was a tough question. Is the axiom of choice true? For Zermelo, in one way, it remains a tough question, but in another way, he says, here's a definite question. Does the axiom of choice follow from these axioms? Now, that one he couldn't answer yet. But there's another one. What about the well-ordering theorem? The well-ordering theorem that every set can be well-ordered. Does that follow? What's the relation between well-ordered and the axiom of choice? What Zermelo did was said, from these axioms of set theory, plus the axiom of choice, I can prove the well-ordering theorem. So this is a definite question. You can't believe these axioms without the well-ordering theorem because there's a proof. And now he's making set theory a definite subject with specific axioms and actual proofs, which doesn't change the question of what's true and what's not true, but it does change the way you can talk about it. We've got specific questions we can ask now. And this, I believe, was his second paper doing that, which is much better than the first. The first was already good, but he was the first person to do anything like this. So of course his second try was a lot better than his first try. And he's explaining to people because nobody knows what set theory is yet. Zermelo is sort of deciding what set theory is. He is the one whose view that they got accepted. So he has to tell them what this is. Also in 1908, this is published in the Mathematische Annalen, which there's no use translating that into English. In English it would be the Annals of Mathematics, but there's a different term called the Annals of Mathematics. So this is the most prestigious math journal in the world, and it's about all of math. He's not writing for set theorists, because there are no set theorists yet. So writing to all the best mathematicians in the world, he says, set theory is that branch of mathematics whose task is to investigate mathematically, that is in precise terms. Let's give precise axioms and precise proofs, which won't change the truth, but might change our insight into the truth. investigate mathematically the fundamental notions, number, order, function, taking them in their pristine, simple form to develop thereby the logical foundations of all of arithmetic and analysis. Zermelo led to huge progress, real progress. This was a brilliant piece of work, a brilliant undertaking. Notice that for him, but when he says foundations of arithmetic and analysis, he means all of mathematics. He's not saying, I'm not going to do abstract algebra. It hasn't occurred to him that abstract algebra could be outside of those things. I mean, he knows some abstract algebra, Zermelo specifically. I think Zermelo may have been the first person to give the abstract axioms for a ring. I'm not sure. Anyway, Zermelo knew some, but it was brand new stuff. He doesn't think of it. He doesn't think that differential geometry is a different thing from analysis. He doesn't think topology is a different thing because they're too new. When he says arithmetic and analysis, on one hand, he means all of mathematics, but he really thinks that's going to be pretty much arithmetic and analysis. From our point of view, of course, arithmetic and analysis are a tiny fragment of what set theory does. But that's his picture. It led to real progress, but what I want to take seriously here, functions as sets of ordered pairs. I had that ZFC definition of function up on the board the other day. I won't recover that one as a slide. So we want to investigate the notion of function in its pristine, simple form. We say a function f from A to B is a subset and I'll write gamma of f, the graph of f. People often talk about the graph of f. Is a subset of A cross B. Intuitively, it's the set of all pairs, an element of A, and the value of F at that element. Where A cross B is the set of all pairs, AB, with A an element of A, and B an element of B, little b, small b, an element of b. This one is very dark either. It's a specific, yeah, well. Such that for every A element of big A, there is exactly one B element of big B such that the pair AB is an element of the graph of F, where an ordered pair AB is the set containing the set whose only elements are A and B, and the set whose only element is A. This, he's telling us, is the pristine, simple form of function. This was huge progress. I'm not trying to make fun of Zermelo or complain about him. This was huge progress. And it led to huge progress. When I say it led to huge progress, I don't just mean the progress on Zermelo-Fraenkel set theory. It led to other progress too. Other people learn from this and go on. This is his candidate for the pristine simple form of function. Our candidate for the pristine simple form of function is that functions First of all, there are identity functions, and functions that match up have composites. That's what we say is a pristine simple form of function. You know how to compose them. You know they're identity functions. That's our definition of a function. Now, if you want specifically a function on sets, you have to know what sets are. But the truth is to do this stuff, you have to know what sets are in this theory too. I don't think any set theorist would say this anymore, because this isn't what Zermelo-Fraenkel set theory achieves. The Zermelo-Fraenkel set theory definition of function is not the pristine simple form of function. When I've studied textbooks, I've looked at, I showed you what Lang says about functions. Lang gives you, let's call that the pristine simple form. A function has values. That's what Lang says. It's all he feels he needs to say for his algebra book. Munker's topology says you could think of a function this way, but most mathematicians don't. I'm not saying this wasn't progress. This analysis was huge progress. But we can no longer regard it as a pristine, simple notion of function. What is the pristine, simple notion of number? Zermelo tells us the pristine simple notion of number is that 0 is the empty set, and for any number n, the successor of n is n union singleton n. Now you can ask your mathematician friends whether that's their notion of number or not. I think that's not their notion of number. In categorical set theory, we say here's the pristine simple notion of number. One of them is 0. Every number has a successor. And really, any time that you've picked an element of a set, and you've picked a function that takes elements of that set to new elements, you can define a function from numbers to there that gives you f of 0, then f of 1, then f of 2. We say the pristine simple notion is numbers, one of them is 0, they have successors, and you can define functions on them by iteration. I just think that's a better candidate for the pristine simple form of number than the von Neumann ordinals. Actually, I gave the von Neumann definition of successor. Remember, this isn't the definition Zermelo gave. No, Zermelo said the successor of n is just singleton n.
Here, f is for the extra, so more you the function, the use of natural numbers to define.
I'm specifying what's universal about the natural numbers. I'm saying that there's the simple notion of natural numbers is not just what they do themselves. It's that they can track iterations of anything. The simple notion of number is that they track iterations. Anytime you have an iteration and a starting point, numbers can track that iteration. Now you're right. This isn't self-contained the way his is. But every mathematician knows this, and almost nobody knows this. In fact, only a handful of logicians know this one anymore, because this isn't the definition we use today. We know the one I had written up there before with the von Neumann. This is not pristine and simple. The very fact that you have to choose between the two definitions, which is the point of Benaceref's famous paper, that we can define natural numbers either of these two ways, and it makes no difference, so neither of them can really be the notion of number. Wow, I just put that together talking now. I have to thank the organizers for giving me the occasion to think of that. Benaceref's famous paper said that numbers as Zermelo ordinals can't be the simple pure form of numbers, because numbers as von Neumann ordinals have just as good a claim, and they can't both be, so they must both have a bad claim. But Nasser have never asked whether the fact that natural numbers track iteration is the pristine form of the notion, because he never heard that you can define them that way. But this is essentially how Dedekind did define them in his famous paper. Was sind und was sollen die Zahlen? You have to say it in German because it doesn't translate into English very well. I don't know whether it would translate into Chinese. It's a subtle question. What are numbers and what should they be? What must they be? Is that Zolan is hard to translate into English. And my Chinese is just not good enough to know what it is. It's also fun to say was sind und was sollen. So I really want to stress, this was real progress, but we can no longer believe that Zermelo-Frankel set theory is revealing this pristine simple form of those things. A lot of people can't believe the categorical set theory is either, but I will point out that most of those people don't know any categorical set theory. They're just pretty sure that if they did know, it wouldn't help. They could be right, but they don't know categorical set theory. And also, the developing of foundations of arithmetic and analysis remains really important. The whole project of reverse mathematics. The whole point of the project of reverse mathematics is to say, what matters most about mathematics today, to this very day, is the arithmetic and analysis. The concrete mathematics. The stuff that you can do in second order arithmetic. And that's a grand program. But we do also have abstract algebra. We also have algebraic geometry. We really do have substantial parts of math today that go beyond arithmetic and analysis. The purpose is not to go beyond arithmetic and analysis. It's to reveal facts of arithmetic. But the methods really do go beyond what Zermelo meant by arithmetic and analysis. Georg Kreisel, he's Austrian, but another German speaker, so there's no E on the name George. Georg Kreisel said, foundations provide an analysis of practice. Okay, now the whole point here is not the pristine simple form. We're going to analyze it. In fact, Kreisel, I'm afraid if you showed Kreisel that Zermelo quote, I think Kreisel has passed now, but someone in the passed last year. But if you had shown this to him, he'd have said, no, I'm not interested in the simple pristine form. I'm interested in analyzing. I'm interested in finding out what all is in there. To deserve the name foundations, this must be expected to introduce notions which do not occur in practice. Kreisel is saying, of course our foundations isn't just the stuff that mathematicians use every day. It wasn't meant to be what they do every day. If I was trying to do what mathematicians do every day, I would be solving differential equations, not writing about set theory. It's not meant this. The point is not to do what they do every day. The point is to analyze what they do every day in ways that they haven't thought of, because otherwise they would have done it. So it must be expected to introduce notions which do not occur in practice. Forcing. Most mathematicians have no idea what forcing is. They have a vague idea what it achieves. They don't know. They can't define it. Wouldn't be expected to. If you're trying to learn differential geometry, don't brush up on your forcing first. Differential geometry is a different thing. But forcing is the most revealing practice in set theory in the last 60 years because it's doing a different thing. It's analyzing the terms that occur in practice. Primarily continuum was the goal, to analyze what is the continuum in ways that hadn't occurred to people doing analysis in geometry. The people in analysis in geometry had generated this question, are there sets intermediate in size between the naturals and the continuum? But none of the stuff they did was able to answer that question, so of course we do stuff they didn't do to answer that question. And I'm not against that sense of foundations, But I wanted to say McLean has a different sense of foundations. These two people are just using foundations in a different sense. They might think that they disagree with each other. But I wonder if Saunders thought he was disagreeing. I knew Saunders and McLean pretty well. Never met with Kreisel. Saunders, I think, would have said that what Kreisel's doing is okay, but it's not very interesting to him. So in a way, he's not disagreeing with him. He's just saying, that's not what I want to do. Kreisel, I don't know what he thought about Saunders. I know that Kreisel was very mean and very funny in talking about everyone, including himself. He once wrote, he had an article in a math journal, and so this journal, Math Reviews, that does short reviews of math articles, they sent his article to various people and said, you want to do a blurb about this? And they all said, oh, no, I don't want to write about Kreisel. So they sent it to Kreisel. And he wrote back and said, this article was clearly not ready for publication. There's nothing very important in it about his own article. He was a sharp-tongued guy. So whatever he would have thought, he was a sharp-tongued. But what I want to say to you is, these are two different things you can do, two different things you have to do. I believe a lot of algebraists and geometers think you don't need to do anything but algebra and geometry. They're wrong. You need to do logic too. Logic is an important subject. Logic has revealed things that matter to everyone, but logical analysis using notions that don't occur in practice isn't going to be central to organizing the practice. It has a different role than that. Well, I don't believe anybody today wants to reorganize set theory around the notion of forcing, unless it would be Wooden. Now, Wooden's program might lead to reorganizing set theory around the notion of forcing. I'm blanking on Tony Martin's axiom. Martin's axiom was at one time, certainly that people were proposing axioms for set theory that were oriented around forcing. Whether Martin ever thought it should be added as a new axiom to Zermelo or Frankel, I don't know. Or whether he just thought it was an axiom worth investigating as part of this analysis of practice. Do you know if you ever wanted to add it as an axiom of set theory, or just want to say we'll use it in our investigations?
I don't know much about that.
I don't either.
Don't know the recent development of
Yeah.
this.
But I think Joel David Hampkins, for example, seems to want to add new axioms to set theory, whose purpose is to set up these multiverses and investigate the continuum hypothesis. But I think most people don't want to make forcing, because forcing doesn't occur in most of math, so we don't want it to be part of our basic axioms. Our basic axiom should be about what math is normally about, not forcing. Which does not prevent us from studying forcing axioms, and certainly doesn't prevent us using the notion of forcing, but we don't add it to the foundations of mathematics. So these are just two different things. Now that does bring up an idea which did not occur in practice until logic demanded it. Here's a place where practice ran into ideas that had not come into practice before. And that's large and small categories. So I will say a little bit about that. I promised that on the first day. These are still often ignored in practice. I mentioned that lots of algebra books talk about the category of all groups. Lots of topology books talk about the category of all topological spaces. The most famous topology book ever, well, certainly the most famous in the English language, Kelley's Topology. I had the great privilege to learn topology from Kelley's book when it was only 12 years old. And Kelley's topology, it's famous for having an appendix on set theory. He invents a new set theory that goes a little bit beyond ZFC because he also has some exercises on the category of topological spaces. So he back in 1955 or 57, I forget which, introduces the category of all topological spaces. And he knows that it's too big to be a set. So he introduces what's now called Morse-Kelley set theory. More people, I think, are familiar with von Neumann-Gödel-Bernays set theory. You take ZFC and you add proper classes. You say beside sets, there are proper classes. There is a proper class of all sets. And you can define proper classes in certain ways and you can reason with them. This is not actually stronger than Zermelo-Frankel set theory. It's a little more convenient. It has a finite axiom system. Remember, ZFC does not have a finite axiom set. You need this infinite axiom scheme. By adding these proper classes, you can express things in a finite number of statements about proper classes that now axiomatize the whole theory. But it's not stronger than ZFC because you can't do much with these classes. Morse-Kelley adds those classes and lets you do a lot with them. It is stronger than ZFC. Morse-Kelley proves consistency of Zermelo-Frankel set theory. It takes ZFC and it adds proper classes of sets as legitimate entities. These are now actual things that we talked about in the theory, and we can say so much about them that we can prove consistency of ZFC. So this is stronger than ZFC, because ZFC cannot prove its own consistency.
Could you say again, Professor, what consistency did he prove?
Yeah.
ZFC class.
Yeah, con ZFC is just a statement, right, that ZFC does not derive 0 equals 1. We can state this in ZFC. Right. We can state it in pound arithmetic. Con ZFC is that statement. ZFC can't prove that statement. That's Gödel's incompleteness theorem. But ZFC plus the Morse-Kelley theory of proper classes can prove it. This is strong enough that it can prove con ZFC.
Right.
Of course.
That means the
Now,
consistent of ZFC can be proved in the.
yeah, it can be proved in this whole theory is called Morse-Kelley.
Right.
And Morse-Kelley can prove consistency of ZFC. Of course, it can't prove consistency of Morse-Kelley. That's Gödel's incompleteness theorem. And I just want to compare that to von Neumann-Gödel-Bernays, which gives a weaker theory of proper classes and doesn't prove con ZFC. This theory is stronger and does. But it's still only classes of sets. We do not have classes of classes. Well, I mean, of course we do. We can have them if we want to, but Morse-Kelley doesn't have them. Morse-Kelley stops with just classes of sets. We could go on to have classes of classes, classes of those, and so on. And so Kelley did not ignore the problem I'm talking about. Kelley was aware these things are too big to be sets. So my solution is I'll also talk about proper classes of sets. These are proper classes of sets. Now I can formalize by talking about these things here. So it's not totally ignored, but you know, when I learned topology from Kelley's book, we didn't read that chapter of set theory. It's not ignored in practice. I mean, my point here is that the difference between analysis of concepts and practice is not absolute. They are not separable from each other. They will contact each other over and over again. I want to say there is a difference to keep in mind there, but it's not an absolute separation. So this was a solution to this problem. But advanced books in topology already by 1948. Well, not books on topology, seminar reports on topology out of Paris. Advanced seminar reports on topology by 1948 were also looking at the category of all functors from topological spaces to groups. This is bigger than either one of those. Just the same as 2 to the n is bigger. Well, it's certainly bigger than 2. And it's also bigger than n. Yeah. So already by 1948, this foundation was not exactly sufficient. Depending on how much of this you want to keep. So by 1956, well, clearly by 1961, Alexander Grothendieck was saying, you know what? We want proper classes, classes of classes, classes of those. We want this to go up not just forever. We want this to go up every ordinal number of times. We don't just want to repeat this every finite number of times. We want to repeat this infinitely often and infinitely often. For every ordinal, we want to repeat this. That's the axiom scheme of replacement that lets you do something for every ordinal. He says, you know what? We don't need to put something on top of ZFC. We need to put something inside it. We need to take ZFC plus, there exists a strong inaccessible. That's inconsistency strength. That's not different from an inaccessible cardinal. Today we call this a Grothendieck universe. The idea of a Grothendieck universe, we've got our universe of sets, which we often like to draw as a V. We've got our universe of sets. We say, you know what? One of these is so big that ZFC is already true in it. Not just that this is a model of ZFC. This is a model of ZFC where what looks like membership is membership, and more importantly, what looks like power set is power set. This thing actually contains the empty set. It contains the power set of everything it contains. Whenever it contains a set and a definable relation of its elements to others, it contains a set of all those elements. The actual axiom scheme of replacement is true inside this thing. This thing is what you might have thought was the universe of all sets here. And again, I mean not just a model of that theory. We know, as Colin knew and talks about, but we've known ever since Gödel proved the completeness theorem, if ZFC is consistent, it's got countable models. But in those countable models, what's interpreted as membership isn't really membership. And for sure, what's interpreted as power set is not really power set. But the point is, in this thing, what's interpreted as membership is really membership, and what's interpreted as power set really is power set. So this involves, these are cardinals, a strong inaccessible cardinal. And as a matter of fact, when I met Shishang Wei, he was talking about whether you can prove that these are the smallest cardinals that ZFC does not prove their existence. Intuitively, that's the case. Every set theorist will say, these are the smallest cardinals that ZFC can't prove exist. And if you posit them, that proves consistency of ZFC. But the question was, how do you characterize that statement exactly? And I don't know what answer he came up with. Do you know an answer from this based on this?
I don't know. I don't know.
So Grothendieck's answer is now, and now what we say is, the category of groups, we really don't mean all groups, we mean all the groups that are in this Grothendieck universe. Now that looks like what anybody would have thought was the category of all groups, but we've now got a set theory that says it isn't. Our set theory says one of our sets already looks like what we used to think all the sets there were are. Not just models the same first order statements, but really looks like it's the same thing. So we've got three responses to the problem of large categories. One is ignore it. Lots of math books have that response. Another is add a level of proper classes. That works for some of the problems, many of the problems, but really not all of them. Another is take a Grothendieck universe. That solves all the problems by posing an actually stronger set theory, a set theory that proves consistency of CFC. And here's the terminology I wanted to tell you about. A small category and let me be explicit, this is on set theoretic foundations. Now we're not doing the category of categories as foundations anymore. That was a different response to this. The category of categories as foundations gave a different way of saying, okay, once you've got set, you've got a category of all groups. You can work inside this axiomatic theory and develop it all. But now we're back on set theoretic foundations. A small category A, oh, right, that's how you draw boldface. I've forgotten this. You underline it. When you're writing by hand, boldface is underlined. Yeah. Is a category with a set of arrows. A category that has a set of all arrows is a small category. Now, since every object has an identity arrow, it follows, in at least any set theory other than new foundations, that you also have a set of objects. So I don't have to say set of objects and set of arrows. Saying set of arrows doesn't. So our finite categories are certainly small. The category of finite sets let me put a question mark here. That's not actually a small category. There's a proper class of finite sets. There's a proper class of singleton sets, right? For every set S, there's the singleton of that set. But the category of hereditarily finite sets. Finite sets where all the elements are finite and all of their elements are finite. This is sets of rank less than omega in CFC. That's a finite category. Just calling it finite doesn't make it, but saying sets of rank less than, sets of finite rank. That's a small category. In fact, it's a countable category. Similarly, let's say the category of all finite dimensional real vector spaces. That's not finite. That's not a small category because this is only defined up by isomorphism. But the category of all vector spaces Rn, now that's another countable category. Every finite dimensional real vector space is isomorphic to one of these, but now I've picked a copy. So now there's a small category. What I'm getting at here is in algebraic geometry, very often you have some technical construction where you're going to invoke a category that if you weren't careful, would be a proper class. But by taking this kind of care, you can make it small. By saying, okay, I actually don't want all the things that look like this isomorphism. I just want this kind of them. By just taking a little bit of care, a lot of those categories can be made small. So that's what a small category is. A locally small category may have a proper class of objects, but for any two objects, A and B, there is a set of all arrows from A to B. Now, so category of groups. Proper class category, there's a proper class of groups. But, given any two groups, there's only a set of homomorphisms from the first to the second. So now this gives us some control. We still don't have a set of all objects, but for once we have any set of objects, and the axiom of replacement, if you have a set of objects, that means there's a set of all the arrows between any of them. So it's not just two objects. If you have the axiom scheme of replacement, that means that given any set of objects, there's a set of all arrows between them. And as a technical matter, if, as some of us do, if you sometimes look at set theories that don't have the axiom of replacement, you really shouldn't define locally small this way. You really should say, for any set of objects, there's a set of all the arrows between them. That's the right notion. That's the notion that theorems will hold for. But with replacement, they're equivalent. And then a large category has a proper class of arrows. Well, by this definition, a large category could actually be any of those. If you want, you could rule them out. You could say, it's not worth ruling them out. There is no interest in the idea of a category with a proper class of objects, of which some of those objects have proper class of maps between them. We don't care. We don't want to distinguish those from them. So this is a terminology that's often used. And this really, really matters, because a lot of constructions you want to do, you go into a category, you want to put certain diagrams in that category and take limits of them. I'm not going to define what that means, but by a diagram, I mean, take a bunch of objects and arrows between them, and take a limit. You get something out of that diagram. And in lots of categories, you can always do that when the diagram is small, but not when it's large. For example, in the category of sets, you take any set of sets, they have a union. Any set of sets has a union of them that's a set. But a class of sets may not have a union. Well, the same thing happens, it may not have a set as union. But any set of sets has a set as union. So often, we want to say every small diagram in a category has a limit. Every small diagram has a co-limit. For real, this matters. Saul Pfefferman, in some of his criticisms of categorical foundations, says the category theorists have to admit that it matters whether a category is a set or not. Of course it does. Of course it does. But I will point out, this is coming late on the fourth lecture. This didn't come into discussing the Eilenberg-MacLean axioms. It didn't come into discussing the category of sets or the category of categories. This comes up long after you had your foundation. Within a foundation, you have to know which categories, how that foundation handles different categories. This is not a distinction we had to make in axiomatizing the category of sets and axiomatizing the category of categories. It's a real distinction we want to make in practice. And I also make the point that this is something people still often ignore in practice. And this means that advanced textbooks on algebraic geometry fairly often make actually false statements that nobody is confused by. Because everybody says, hey, I'm going to stick with small stuff. But they just don't want to talk about it. And Grothendieck, Alexander Grothendieck, I will point out, who created so much of this, was very careful about these things. Grothendieck made sure to get them all right. And people, and sometimes set theorists will say, this is something Penn Maddie feels mathematicians say, I don't need foundations, I know how to work. And she says, you can only say that because there are foundations. You know, I don't know how to design buildings. I walk around through buildings just fine. You can only say that because some people do know how to design them. You know, and the same thing here. People who want to ignore this stuff, one of the reasons they can ignore it is that Alexander Grothendieck didn't ignore it, but he gave a different solution. He doesn't define this. He says a U small category is a category given by sets in universe U. And he has an axiom: every set is an element of some universe. When I drew a picture of a Grothendieck universe, I acted like it was the Grothendieck universe. But Grothendieck actually says, when we're describing our universe, our category, our world of sets, there's a Grothendieck universe in there that looks like the whole world of sets. And it's contained in a Grothendieck universe that also looks like the whole, and it's contained in one. Which means for every larger Grothendieck universe, there's at least one larger inaccessible cardinal. This means there's a proper class of strongly inaccessible cardinals. This is slightly stronger than the strongest set theory that Zermelo pictured. Zermelo actually pictured adding inaccessibles, but he never thought to combine this with the axiom scheme of replacement, and to say, this implies in ZFC, for every ordinal alpha, you know, there's a lot of ordinals. For every ordinal alpha, there is an alpha Grothendieck universe, which, by the way, the cardinal here is an ordinal. So, yeah, this is huge to my imagination. I will mention to the imagination of a set theorist like John Steele, for example, these are small, large cardinals. These are not big, large cardinals. The existence of a single measurable cardinal implies that this is true below that cardinal. It doesn't imply it's true above the cardinal, but the existence of a single measurable implies that this is true below that measurable. So, and as a matter of fact, it's now 5 o'clock, so, okay. Yeah.
但就是我的意思就是翻译成范畴跟翻译成纲的是有什么差别？因为英语单词的话，就是用同一个单词说明它们的性质是不是应该是非常接近的，甚至有同样性质。
是一样的，就是你自己去查那个，就是那个纲的汉语意思和那个范畴的汉语意思，实际上也是就是有一定关系。他想说的那个纲， 就跟那个范畴差不多，就是是一个
这个范畴他要说什么？就同样的，
不好解释，因为这东西就你可以这么想，就是
在他这里一个范畴
就是一种概念，你可以这么想，就和概念差不多，你
不是他不是应该说概念的那个
纲也是概念的意思，就是
不是范畴，就是相当于就是概念的一种形嘛，应该说是。